Hi there. So, my name is Guillermo Gomez. I'm a reliability engineer here at HP, and we are at the Strategic Quality and Reliability Engineering Lab in Houston, Texas. So if you look around, we have all sorts of different capabilities here in order to go and stress and analyze the different systems and products that HP comes out with. So this is all part of the HP Total Test process, about 120,000 hours of testing in order to make sure that you, the customer, get the best product there is. So my job here at HP is to look at the different systems that we put out and try to find different ways that we can go and stress them, ensure that quality standards are met, and make sure that you have the best product available. In other words, I break stuff for a living. So this device is our high-speed camera. Inside this little guy, we have the capability to record video up to 17,000 frames per second. That's 250 times faster than the human eye. Now, why do we need high-speed video here at HP? Let's say I were to grab this unit right here and perform a drop test. Now, when I did that drop, you could probably determine roughly what height I dropped it at, what angle did it land at, but there's a lot of phenomena that can't be seen with the naked eye. And with using high-speed video, we're able to capture those phenomena and send it back to the design team in order to help them understand how to better build a product. This system right here is our tensile tester. Now, a tensile tester is made up of two different components. We have a motorized crane that moves up and down, and we have a transducer here attached to this probe at the end. A transducer is a device that takes a force and turns it into an electrical signal. This way a computer can go and read it. Now, with these two working together, what we can have the computer do is control this system in order to go either apply a certain amount of force or move a certain distance. What this allows us to do is measure force versus displacement relations, and from there understand things like human factors requirements, understanding how clicky a keyboard is or how good it feels to press a button, to mechanical design requirements such as understanding how much force it takes in order to go and bend and deform a certain chassis. With this information, we're able to go design and test different systems in order to make sure they maintain the robustness requirements that they need in the field. So the device we have here is our keyboard cruncher. You can probably guess what it does just by the name. Now, the way the keyboard cruncher works is that we have a bunch of pneumatic plungers here that are pressing on the keyboard or mouse or whatever switch mechanism you want to go and place in here. What this allows us to do is we're able to stress the product and understand how the switch performance is going to be throughout its lifetime. So while it's going through this, we can then go and do human factors analysis in order to understand how springy this switch mechanism will feel, or signal analysis in order to ensure that signal integrity stays robust throughout the product's lifetime. This system right here is our temperature and humidity chamber, also known as an environmental chamber. So not every product we sell at HP is going to be in the lab environment. Some places are going to be a lot hotter, some places are going to be a lot colder, some places a lot more humid, and some places a lot drier. And so because of these different environments, we want to make sure that the product is going to be able to hold up against these different environmental stresses. And with an environmental chamber, we're able to go and simulate those stresses to ensure that the product holds up throughout its lifetime. This system right here is our mineral dust test chamber. Now if we look inside, we see this fine, white, chalky sort of dust. This is magnesium silicate, also known as talc. But unlike your store-bought version of talc, this is a very fine version of it. How fine? About 15 to 20 micron in diameter, roughly the size of a white blood cell. So what do we do with all this dust? We take this dust, fill the chamber with it, from there power on some fans and stir it around. And by stirring the dust around, what we're trying to do is force its way inside of systems in order to identify points of dust ingress, and if the system is meant to be dust tight, find out what points do we need to go and seal in order to make a truly dust tight system. This machine right here is our tumble tester. So the tumble tester is made up of 2 barrels and a motor. And when I press start here, we can see the motor power on, rotate the barrels, and cause the units inside of it to drop over and over again. Now this is supposed to simulate scenarios where, for example, if I were to give this to a kid takes this, throws it in his backpack, throws it in the locker, and from there the unit's going to go through a lot of repeated shocks over and over again, which is different from the single drop tests, because multiple shocks are going to have a different effect than one large drop on the system. So that concludes our tour for today. Thank you for joining me in the Strategic Quality and Reliability Engineering Lab and getting a glimpse into how we at HP put your products to the test in order to make sure we deliver to you a more robust product. This is Guillermo Gomez, signing out.